Okay, let's get started here. I want to start by just announcing that on Tuesday, next Tuesday, we will have Bruce Maggs giving a guest lecture. He's a professor at Duke University, and I've heard him called Professor Network. He knows everything about networks. Really amazing fellow who's going to talk about performance in networks. He's also a tremendously entertaining speaker, as you will see. He's an MIT triple beaver, and for those of you who don't know what that means, he's got 3 degrees from MIT. He's a former vice president of research at Akamai Technologies and helped to found that company, which is now billions of dollars. He's an ACM fellow. He's creator of Avatar, which was one of the early computer
highest grossing movie of all time. Sorry.
It's the what?
I said the highest grossing movie of all time. No.
Yeah, right. No. So actually, he created this game well before the movie. And it's a game that I think at one calculation had consumed over 1 million hours of University of Illinois' computing time by students there, because he had originally started out at Illinois and he transferred into MIT, and he's in the Guinness Book of World Records for the photograph that he took of the world's longest slide rule. He did, so he's very proud of that accomplishment. And he's got many best paper awards, really brilliant. And he's going to talk, as I say, about performance, how you do performance engineering of networks and so forth. Very, very entertaining and valuable talk. So that'll be next Tuesday. So anyway, let's
okay. With that, I'll take it away.
And take it away, Jonathan.
All right. So good to see everybody. Hopefully everybody's holding together in spite of slow and ongoing uncertainty in the world, but we'll get through it. And today we have some more fun stuff to talk about. So this week is all about non-deterministic parallel programming. So last time we talked a lot about synchronization with mutual exclusion primitives, or locks. And today we're going to conclude with the most advanced material. So we'll start out introducing the idea of memory consistency models, which are essential for thinking about how this all works under the covers. And then we're ultimately going to build up to showing how we can build a concurrent data structure without any locks at all. Which, you know, on its face, this sounds kind of amazing, but it turns out that it's possible. And we'll show you how to do that. Okay, so first let's talk a little bit about memory models. So to understand what memory models are all about, let's think about a really simple situation. So let's say we have 2 processors, a processor 0 and processor 1, and 2 addresses in memory, A and B. And A and B both start out with the initial value 0. So then each processor runs a symmetric piece of code. So P0 writes 1 to the address A, the address of A, and loads from the address of B and stores it in the register EBX. And then similarly, but with the A's and B's swapped, P1 writes the value 1 to the address B and loads from A into the register EAX. So now let's think for a second about what could happen here. And in particular, I want to ask the question, is it possible that processor 0's EBX register and processor 1's EAX register both contain the value 0 after these, the processors have both executed their corresponding code? So we have a poll for this, and I'd like to see what people think. Few responses. Don't be shy. Seems like mostly yes and some no. It seems like significant majority of people say yes. Although
they're only saying yes because they think it's
because they suspect it's a trick question. Exactly. More people are saying no. And in a sense, it is a trick question because the answer is it depends. And in particular, it depends on the memory model. And the memory models are all about the rules or semantics for how memory operations behave in a computer system with multiple processors. And we're going to talk about some memory models where yes, this would be true, and some where no, it would not be true. Okay, so the first memory model I want to introduce is called sequential consistency. And this is a natural way of reasoning about memory, and it's probably what you already assume most of the time when thinking about these simple parallel program snippets. So credit to those of you who said no. There's a good argument made by Turing Award winners that it might be a good ideal for computer systems that no, this is not possible. So sequential consistency, as defined by Leslie Lamport in the late 1970s, Lamport's definition says that a memory model is sequentially consistent if the result of any execution is the same as if the operations on all of the processors were executed in some globally sequential order, and the operations of each individual processor appear to have executed in the sequence, in that global sequence, in the order specified by each individual processor's program. So under this model, the sequence of instructions as defined by a processor's program are interleaved with the corresponding sequences defined by other processors' programs to produce a global linear order of all instructions. So we can effectively reorder the instructions of executing on one processor with respect to those executing on another processor, but we're not in particular reordering things within what's happening on any one processor. So under this global linear order, a load instruction from address X always receives the value stored to X by the most recent store instruction that precedes that load in the global order. And this model allows the hardware or the underlying implementation to do whatever it wants, but it must appear as though the loads and stores obey some global linear order. And that's basically where the name comes from. They're consistent with a global sequential ordering of all the operations. Okay, so with that, let's look back at our simple example situation. And let's try to answer our question about whether both processors could wind up reading 0 if we assume this sequential consistency model for our memory. So if we identify the 4 different operations here by the numbers 1 through 4, so this first instruction is 1, 1, 2, 3, 4 numbered here. With that numbering, we can make a table where we enumerate all possible interleavings. So these interleavings are going down, different interleavings going across, and the sequence of operations within a given interleaving going down in this table. So under sequential consistency, there are 6 possible interleavings. In general, the total number of permutations of these 4 instructions would be 4 factorial, which is like 24. But we only get 6 possible interleavings under sequential consistency, and that's because sequential consistency requires 1 to go before 2, and it requires 3 to go before 4. So now we can think through what would happen in each case. So for example, in this first case, we do 1, then 2, then 3, then 4. So we first write 1 to A, then we load B, which is currently going to be 0. Then we write 1 to B, and then load A, which is currently going to be 1. So we'll get EAX is 1 and EBX is 0. Similarly, with a slightly different interleaving where we go 1, 3, 2, 4, both of the writes are going to happen before both of the reads. So they're both going to wind up reading 1. Again, a number of the other variants, both of the writes happen first. And then there's another condition where we do 3, then 4, then 1, then 2. And in this case, we'll also only get 1 of the writes before the corresponding read. So EAX will be 0 and EBX will be 1. Okay, so just looking at this, enumeration of all possible interleavings, we can see that sequential consistency, under sequential consistency, no execution is going to end with EAX and EBX both being 0. All right, so a useful thing to think about, or a useful tool to have in reasoning about memory consistency models is the idea of a happens before relation. And so intuitively, the happens before relation tells us which memory operations appear to happen before which others. And here I'm going to denote the happens before relation by this arrow. So X arrow Y says that X happens before Y. All right, so now there's some key properties of the happens before relation in the case of sequential consistency. So the first is that the happens before relation is linear. And by linear, we mean that for any two distinct instructions, X and Y, either X happens before Y or Y happens before X. And if we think about that over all of the operations, it means that that the happens before relation defines a total order of complete linearization of all of the operations. The second key characteristic of sequential consistency from this perspective is that that happens before relation always respects the processor order, which is the order of the instructions within each processor. So you can think of the order of instructions within each processor's program as being a partial order constraint on the instructions, just those instructions within that processor. And the global linear order has to respect the partial order for each processor's instructions. Then the implications of this for our memory model, the kind of the meaning of the happens before relation in terms of the semantics of what we can observe are that a load from a location in memory is always going to read the value written by the most recent store to that same location, where by most recent, I mean the last one to happen before the load according to the happens before relation. And then for the memory resulting from an execution to be sequentially consistent, there must exist such a linear order that yields that memory state. All right. So now using that strong consistency model of sequential consistency, let's look at how we can achieve first just basic mutual exclusion without having to use locks. And specifically, we're going to build a protocol that provides mutual exclusion using only atomic loads and stores. So if you recall from last time, a critical section is a piece of code or some piece of logic that accesses a shared data structure that must not be accessed by two or more threads at the same time. And we call the property of enforcing that mutual exclusion. So no two pieces of code are allowed to be interacting with that shared data structure at the same time. So importantly, most implementations of mutual exclusion on real systems employ some kind of atomic read, modify, write instructions or relatively similar equivalent things to implement locks. So for example, last time we used the x86 exchange operation that atomically reads and writes a value, swaps a value between memory and registers to build our locks. And there's a bunch of other similar atomic instructions that you'll see on different architectures, including x86 and other things like test and set, compare and swap, which in particular we'll talk more about later today, or some even fancier ones like load linked store conditional. The fundamental thing with all of these is that they have this kind of read, modify, write structure where they're atomically doing what in terms of just basic load and store instructions would be multiple separate operations, but they're making sure that those all work atomically together. So it's either a combination of an atomic read, an atomic combination of a read and a write, or of a read, some logic, or computation and a write. All right, so most implementations of mutual exclusion use one of these atomic read, modify, write operations. But one question you might want to ask is, is that fundamentally necessary? So is it possible that we might be able to build a mutual exclusion scheme using just loads and stores as the only memory operations. I'm curious what everyone thinks. If anyone wants to actually, I can't remember if I have a poll here. I'm sorry. I think I don't.
Oh, there is one.
Oh, there is one. Okay, sorry. There we go. Great. Sorry, I should make notes on my slides where I have polls. My apologies. It seems like getting kind of an even race between yeses and nos. Abe observes that it's because of how the loads and stores are structured. I'm curious what you mean by structured, like how we order them, or the question here is, using any combination of an arbitrary number of loads and stores, any protocol we could devise, potentially doing a whole bunch of different loads and stores, is it possible to implement mutual exclusion without requiring one of these more complicated atomic operations? Seems like we're at about a toss-up. And again, in some sense, the answer is it depends. But in this world we've been talking about right now, where we have sequential consistency, it turns out that yes, it is possible. So I think the first proof of this is due to Decker and Dijkstra, who are studying it in the context of concurrent threads on a single serial computer. But in general, it is possible as long as the memory model is sequentially consistent. And we'll see what that means right now. So yeah, so let's see how that could work. And we're actually going to look not at Decker and Dijkstra, but at a much simpler algorithm due to Peterson. So the setup of the problem I want to look at is a rather ridiculous incarnation of Alice and Bob. So we have Alice and Bob both seemingly on drugs, very excited to be interacting with this shared widget X. Alice wants to frob the widget. Bob wants to borf it, and the widget requires mutual exclusion. So it can't be both frobbed and borfed at the same time. And I emphasize that I take no credit for the design of this example. Okay, so now let's look at some code for how we could do this using Peterson's algorithm. So in C, the basic setup we need is this. So we have our widget object X, that's the variable we want to protect. We're going to use a few Booleans, A wants and B wants, which both are initialized to false. You can read this as Alice wants to get into the critical section and Bob wants to get into the critical section. And then we'll have one more variable, which is a flag or an enum for whose turn it is. Is it Alice's turn or Bob's turn? And then the core code of the algorithm looks like this. So Alice and Bob are both going to follow symmetric versions of this same protocol, where when they want to try to get into the critical section, Alice is going to say A wants equals true. So Alice wants to access the widget. But then somewhat counterintuitively, Alice is going to very politely yield and say, I think it should be Bob's turn. Then Alice is going to spin on this condition. As long as it's both Bob's turn and Bob wants to be in the critical section, Alice is just going to spin and wait for one of those conditions to change. Similarly, Bob is going to do the same thing with the A's and B's swap. So Bob's going to say, I want to be in the critical section, but it should be Alice's turn. And I'm going to wait until either it's not Alice's turn or Alice doesn't want to be there. And then it'll be safe for me to proceed in the critical section. And then each one is going to set wants back to false when they're done. All right. And potentially they're running this in some kind of a loop where they're repeatedly interacting with the widget. Okay, so now let's think a little bit about how this works. So first, at an intuitive level, if we think about the case where both Alice and Bob are trying to enter the critical section at the same time, then we can if we think through those steps, what's going to happen is whoever writes last to this turn variable is going to wind up spinning while the other one makes progress. So if Alice gets up to this point first, and then Bob runs through and sets turn back to A, Alice is going to be able to fall through into the critical section because turn is going to be A, so it's going to be safe for her to proceed, while Bob is going to spin. Or symmetrically, if Alice sets the turn last, it'll be Bob's turn, and Alice will spin while Bob works. If only Alice tries to enter the critical section, she can trivially progress since B wants is going to be false, or similarly for Bob. So if only one of them is trying to get in, they'll hand the turn over, but it won't matter because the other player won't be in the condition of wanting access to the critical section. So it'll be safe for them to enter. All right. So that's the basic intuition for how this works, but we can be a little bit more precise. And specifically, we can prove that Peterson's algorithm achieves mutual exclusion on the critical section. And the proof is going to work like this. It's going to be a proof by contradiction. So we're going to assume for the purpose of contradiction that both Alice and Bob get into the critical section at the same time. That's basically the violation of mutual exclusion. And we're going to consider the most recent time that each of them executed the code right before entering the critical section. And then from that, we'll be able to derive a contradiction and say that, after executing that code, it's not possible for both of them to get into the critical section together. Okay, so back to the code. If you note that both Alice and Bob must, by the time they're in the critical section, they must have executed these three statements that make up the guard. So now, without loss of generality, we're going to assume that Bob was the last one to write to turn. So Bob's right to turn happens after Alice's. So using our happens before notation, we're saying Alice writes B to turn before Bob writes A to turn. So that gives us this partial order in the happens before relation. Now, saying without loss of generality is an easy thing to say, but in general, that's a useful technique when we have this sort of strong symmetry between different facets of our problem. So intuitively, everything in Alice and Bob is so symmetric that it's pretty easy to see that we could say that Alice was the last to write, swap all of our Alice's and Bob's, and all the logic would follow through the same way. So we're just going to focus on this case where Bob was the last one to write to turn. All right. So then we also have the partial order implied by Alice's program order. So, and this is, again, we're assuming sequential consistency. So sequential consistency says that all of Alice's reads and writes to memory have to happen in her program order. And so just looking at these first statements, we know that Alice is going to set A want to true before she sets turn to B. And then looking at Bob's program order, we know that Bob is going to set turn to A before he reads the values of A wants or turn in this spin guard before the critical section. Okay, so let's look at what those constraints imply about the order of these operations across the two threads. So we know that first, just looking at these happens before relations we've laid down, we know that first Alice is going to set A wants to true. Then she's going to set turn to B. Then Bob is going to set turn to A. That relationship was the thing that we were basically assuming at the beginning. Then Bob is going to read A wants and read turn. So that's the order in which this subset of the operations in the two programs is going to happen. And so now the question we need to ask to understand what could possibly happen is, what did Bob read? Because whether or not Bob proceeds into the critical section depends on what he read right there. So what do people think? What values of A wants and turn does Bob read in these steps 4 and 5? Anybody want to hazard a guess? Are A wants and turn, is A wants true or false, and is turn A or B? Few guesses coming in. So we have guesses for true in B, true in A, true in A. Or B. So A wants is definitely going to be true. Yeah, some vacillation on A and B. And turn is going to be A, because we know that this right to turn happened after this one. All right. So what does that mean? It means that Bob should spin and not enter the critical section. So with this sequence of operations under sequential consistency, it's not possible for Bob to enter the critical section. But we started out assuming for the purposes of contradiction that they were both in the critical section, but we've just derived a logical contradiction here. So that's not possible. So if Bob goes second, it's not possible for him to enter the critical section until Alice finishes and sets A-want back to false. All right. So that's a proof that Peterson's algorithm can enforce mutual exclusion. It turns out we can also prove that it guarantees starvation freedom. So that's the property that while Alice wants to, if you assume both of them are running in loops, repeatedly trying to enter the critical section, while Alice wants to enter her critical section, Bob can't execute it twice in a row, and vice versa. We're going to leave this proof as an exercise for the reader. You can look it up in various references or find it online, but it's a nice property to know of this algorithm. All right. So now let's look at what happens in more relaxed consistency models. So far we've been entirely talking about the memory model of sequential consistency. And it's simple and easy to reason about and actually really powerful, which is why it's possible for us to do things like build mutual exclusion just using regular loads and stores. The real problem is that no processors that you're likely to use actually support this model. So modern day processors generally all implement some form of relaxed consistency. And not too surprisingly, this is all because of issues of performance. So both the hardware and it turns out even the compilers for low-level languages like C are somewhat free to reorder instructions in ways that can be surprising. Okay, so let's think back to our simple example from the beginning. So remember, we had these two different programs where we were first storing a value and then reading a different value. So a question we might ask, I was just saying that realistic systems have more relaxed consistency models. So sequential consistency requires that this store would always happen before this load, that the ultimate global ordering of operations would be such that this store happens before this load. But if real hardware and real compilers are potentially reordering things for performance, what do we think are some reasons why it might be valuable for a compiler or hardware to reorder these operations with respect to each other? Does anybody have any thoughts? So I guess I've already alluded to the fact that it's performance broadly, but I'm curious if anybody has thoughts on some of the reasons specifically why that might be useful. Maybe? People thinking? Yeah, locally, okay, some guesses that relates to caching or maybe like what's in the registers. From the perspective of the compiler, it can be useful to be able to reorder things or even eliminate loads entirely because we previously loaded from the same value and assume that we have that value in registers. At the level of hardware, in particular, a big reason why we want to reorder loads earlier in a program is because loads are often on the critical path of performance. So if you think about what loads and stores imply in the processor, stores are kind of a fire and forget operation. So I can throw a store off to the memory system, but I don't necessarily need to wait before I proceed further. frequently a store is the output of some computation, whereas a load is the input to later computations. So it's really common that the operations following a load need to use the result of that load. So if we're loading a value from memory and then adding something to it, we can't start doing that add until the load has completed. Whereas if we add two values and then store them, often we can go on and do whatever else without waiting for that store to completely commit to memory. Loads are often the critical path in programs that can cause potential stalls. And so it can be really useful to reorder loads to happen earlier or allow other operations to proceed while loads are still in flight to cover the latency of fetching values from memory. Okay, so that's a little bit about why we might want to be able to reorder these instructions. So now the other obvious question is, when can we do it? So when is it safe for the hardware or compiler to perform this reordering? I wonder if anybody has thoughts on what some of the obvious constraints are here. When is it going to be safe for us to perform this reordering? What conditions might we have to assume? So if we just think about this one program and ignore parallelism, do we think that this, like if I'm just compiling straight line code running on one processor, is it safe to reorder this load before this store? Yeah, exactly. So multiple people are hitting on the fact that from the perspective of this one thread of execution, it seems like a perfectly reasonable thing to do, because the store and the load are dealing with different memory addresses. They don't really interact with each other. So it doesn't seem like there's any big reason why we shouldn't be able to, do the load in any order with respect to the store, because they don't interact. They don't touch the same value in memory. But from the standpoint of the parallel settings we're talking about, there's a separate critical constraint, which is also that there's no concurrency. So if we're trying, for example, to maintain sequential consistency, this reordering is not going to be safe, and we've seen how with multiple, or I guess we'll unpack a little more in a minute, how if we have multiple programs running on separate processors, reordering locally may not be visible from the standpoint of any one of them, but it may mean that the total order of apparent memory operations breaks sequential consistency, which might break our ability to do some of the synchronization schemes we've talked about. Okay, so to motivate relaxed memory models a little bit more, let's look under the covers of the memory system in a modern processor. So at a high level, it looks something like this. So because the processor can often issue stores faster than, so we have a processor connected to a memory system over some kind of interconnector network, like on-chip network. And because the processor can issue stores faster than the network can handle them, it generally has some kind of a store buffer. So this, you can think of as basically just like a FIFO that lets it queue up some number of stores locally faster than the memory system can consume them without having to stall. In the aggregate throughput isn't going to be any higher, but it means that if our processor is alternating between doing a bunch of little stores and then doing some compute work and doing a bunch more stores, that burst of stores can go faster than the memory system could keep up with by itself, and they'll just get queued up in the buffer and flushed out later while we're doing other things. So this is really useful for performance, but the processor is not generally going to buffer all the memory requests in this queue. And specifically, since, like I talked about a minute ago, a load can stall the processor very often until it's satisfied, loads usually take priority, and they're allowed to bypass the store buffer. So we're not just queuing every request to the memory in order. We're instead queuing up the stores, making sure they happen in order, at least with respect to the addresses that they're, the ones that are touching the same address. But the stores are allowed to jump ahead of the line and go straight to the memory system, because we don't want to introduce extra latency and stall the processor for longer. Now, if you think about what might happen if the loads that we want to bypass are for addresses that are still stuck in the store buffer, this isn't, this isn't safe by itself. So it's not safe for all loads to completely bypass the store buffer. And specifically, if a load address matches an address that's in the store buffer will just immediately return the result. So loads first check the store buffer before going to the memory system to make sure that we get consistent results, consistently ordered results for any individual address. But in general, this means that loads can bypass stores to a different address. So just this basic interface to the memory system, which is really, really common, means that loads and stores, loads can be reordered ahead of stores. There's other computer architecture issues that cause similar kinds of effective reordering, but even just this basic interface to the memory system means that loads and stores can get reordered with respect to each other. All right, so that's some of the architectural motivation for weaker memory consistency models. So now I want to talk a little bit about the real memory model that we have on the x86 processors that we program in this class. So x86, modern x86 supports a weaker memory model than sequential consistency, and it's something called total store order, or you might hear it also referred to as TSO. So under the TSO model, the stores in a program are executed on the processor in a global total order. So if we consider just the store instructions, they follow something kind of like sequential consistency. And an x86 machine, but at the same time, an x86 machine does allow later load instructions to be executed before earlier stores, as long as they aren't touching the same address. And so because of that reordering of loads before stores, x86 does not implement sequential consistency. All right, so we can unpack TSO more concretely into these specific properties. So the first is that loads are not reordered with other loads. Or sorry, locally from the perspective of a single processor's execution, loads are not reordered with respect to other loads. So we can't do that. Second, stores are not reordered with respect to stores, so we can't do that. Stores are not reordered before prior loads, so we can't do that. But the critical optimization that is allowed is that loads may be reordered before prior stores to different memory locations, but not any prior stores with the same memory location. And because of that, total store ordering is weaker than sequential consistency. That's the key point at which they differ. There's some, there's a few additional details. So loads and stores are not reordered with respect to a group of instructions that are considered synchronization or lock instructions. And then globally across processors, stores to the same memory location have to respect a single global total order. Hence the name total store order. Lock instructions also have to respect a global total order. And there's a notion of the memory ordering preserving some sense of transitive visibility of stores with respect to loads. Okay. So now let's think a little bit about the implications of that for the potential behavior of our simple introductory example. So if we logically number the different instructions like before, 1, 2, 3, 4, under our weaker memory model, so with the TSO model we've been talking about, it's perfectly legal to move both of the loads before both of the stores. So in this case, we move 2 before 1 and 4 before 3. And if we think about an ordering like this, it clearly will give us the counterintuitive result that both EAX and EBX will have loaded 0. So we're doing the loads before we do the writes, and those values just trivially are sitting there storing 0. So this kind of reordering violates sequential consistency. And again, why do we do this if it makes reasoning about programs so hard? As with many things at the level of computer architecture and many things we worry about in this class, the reason is performance. Okay, So now let's think about, actually, maybe I'll stop there for questions and take a brief breath. I realize I'm blitzing through maybe a little bit faster than usual. Does anybody have any questions on stuff we've seen so far? Are memory models something people have seen in other contexts? Maybe, maybe not. Certainly when I was at most of your stage in my own career, they were not something I understood. I think it was like a phrase I had heard, but had no idea what this was all about, or where the complexity was. All right, so I just explained a bit what the memory model on a real x86 machine is. And so now I want to think a bit about the implications of this kind of weaker consistency like TSO for the Peterson's algorithm scheme we were using for getting mutual exclusion with just plain loads and stores. So we saw before how sequential consistency meant that just regular loads and stores were sufficient for this simple protocol to get mutual exclusion. But under TSO, or under most real-world consistency models, the loads, and in particular these loads of A wants and B wants, are free to be reordered before the corresponding stores. And if that happens, both A wants and B wants are false, and both, assuming Alice and Bob are racing up to enter the critical section, they both do these corresponding reads of whether the other person wants in before they set their own wants value to true. By the time they're then using that condition in this while loop, it's going to be false, and they're going to both fall straight through into the critical section. So both Alice and Bob are potentially able to enter the critical section simultaneously, depending on the exact scheduling of these operations. And this is basically just an issue of the core ordering constraints that we were assuming in our proof of safety under sequential consistency. Some of those core ordering constraints are now relaxed, and so it's perfectly possible to get orders that are inconsistent and where both can fall straight into the critical section. Now, weaker memory consistency models make real processors harder to deal with in ways like this. But it turns out that we're not totally out of luck. So regular load instructions can be reordered arbitrarily early with respect to stores to other addresses. That's the core, the core weakening of these memory models. But it turns out that we can enforce stronger ordering at specific points in our program using special memory fence or barrier instructions. So a memory fence or a memory barrier is a hardware action that enforces an ordering constraint between the instructions before the fence and the instructions after the fence. So in general, on either side of the fence, we have the kind of weak ordering constraints that we talked about. But across the fence, everything that happens before has to appear to have occurred before everything that happens after the fence. So memory fences can be issued explicitly as instructions. So in x86, we have an instruction called mfence, conveniently, that does exactly this. Or they're also often performed implicitly by other locking, exchanging, or atomic synchronizing type of instructions. In the OpenSilk LLVM compiler infrastructure that we have that implements the C11 standard, so what you're using in this class, the compiler implements a memory fence in a portable way using the atomic thread fence function defined in the C11 standard atomic header. And then, so it's relatively easy to do this without actually having to call mfence directly. This atomic thread fence is portable across different architectures, but on x86 will correspond to like an mfence instruction. And then a little note about performance. You can think of the typical cost of a memory fence as being somewhat comparable to something like an L2 cache access, so like a few tens of cycles. So it's pretty expensive compared to an add or a regular load, but it's not too horrible, and on real implementations, this cost has actually been going down somewhat slowly over time. They've been optimizing them better. Okay, so back to Peterson's algorithm. Our old version no longer worked under TSO. So this was our old code, which breaks down with weaker TSO consistency. But we can extend it a little bit using explicit memory fences to restore sequential consistency at the critical point in the programs. And in particular, we can make sure that our check in the guard of the critical section happens after the writes to the corresponding flags. Turns out this is not a totally sufficient answer. This is, if the compiler spit out instructions in this order with an M fence here, this would be sufficient. But the C compiler also has a weak memory model, which allows a fair amount of reordering. And so it turns out you also need to fight the compiler even harder to make sure it doesn't do anything too crazy. So a full implementation in classical C would look something like this. So we have to declare, related to some of the things people were guessing earlier about potential reordering with compiler optimizations, we have to declare all of these variables to be volatile. That means that the compiler is not allowed to just store them in a register and reuse them locally from there. Every time you touch them, it has to actually check for potentially new values in memory, which is important for communicating between the two separate threads. And then, depending on the definition of Frob and Borf, that also might be allowed to be reordered arbitrarily with respect to everything else. So there's some various basically hacks where you can insert volatile code blocks, meaning non-reorderable code blocks, and these are effectively barriers that prevent code of any kind from being reordered across these lines. So these are in some senses compiler fences that prevent any code ordering, just like this is a memory fence that prevents reordering of loads and stores. That's really ugly and seems kind of hackish. So the C11 language standard actually defines its own much more clear weak memory model in which you can explicitly control both hardware and compiler reordering of memory operations using more of what you see here. So you can declare variables as atomic and then load and store them using explicit atomic load and atomic store helper functions or kind of intrinsic functions. You can look up the standard reference for C11. This is kind of verbose, but at least is portable and safe and has a well-defined memory model. All right, so with strong consistency and specifically sequential consistency, we can get mutual exclusion with just plain loads and stores. So with just two threads, like in our Alice and Bob example, that's easy enough. But if you think of how Peterson's algorithm would generalize, we need different variables for each thread that wants to interact with the critical section. So we had this Alice's like A wants and B wants. We generalized this to lots of threads. We'd have A wants, B wants, C wants, D wants, etc. And it turns out that we can prove, and Burns and Lynch did, that any n-thread deadlock-free mutual exclusion algorithm that uses only simple loads and stores requires at least order n space. So that's like, having to have a separate guard variable for every single thread potentially entering the critical section. And we can also prove that any n-thread deadlock-free mutual exclusion algorithm on a modern machine with these weaker consistency models fundamentally must use some kind of expensive operation, such as a memory fence or another memory atomic, like compare and swap, which we'll talk about right now. And these basic fundamental properties are the reasons why, even though we can, given sequential consistency, we can implement mutual exclusion using a simple scheme like Peterson's algorithm, why these more advanced, more complicated atomic instructions are really useful in real systems. Okay, so now I want to take a 2-minute breather and then come back and talk about compare and swap. All right. So now that we understand the memory models of our machines and some of their implications, Next, let's start looking at some of the more advanced features that we can use to build lock-free algorithms. So the key toolbox that we're going to focus on using now are our classic load and store instructions, like you've had since you first thought about what a processor does. But we're critically also going to add one more, the compare and swap or CAS instruction. So this is a really common and powerful atomic operation, and you can find variants of this on lots of different architectures. And it's really useful primitive for building lock-free algorithms, which we'll see. So what is compare and swap? So on x86, you can get at this operation in the form of the compare exchange instruction. And there's a portable version in the C11 standard atomic header called atomic compare exchange strong that can operate on portably on various integer types up to some width. And what it does under the covers, you can think of as semantically corresponding to some simple logic like this. So compare and swap takes a pointer, which we'll call x, and two values, an old value and a new value, and it returns a bool, like a condition flag. And what it does internally is it reads the value at that pointer and checks whether it's equal to the value old. If it is, it sets the value of that memory address to the value new and returns the flag true. And if it wasn't equal to the value old, it doesn't update anything and just exits with the flag false. Importantly, it executes all of this atomically. So there's no potential interleaving of other loads and stores between the different steps of this operation. It's all one big compound thing that always executes atomically with respect to everything else that might touch that address. And on x86, and I think elsewhere often, it also implies a memory fence. So loads and stores that happen before will occur before loads and stores that happen after. So using compare and swap, it turns out to be really easy to build things like mutexes. Mutexes, kind of like the one we saw last time and like this one I'm defining right here, are nice because unlike the Peterson's algorithm scheme, which requires at least order n memory for n threads, an n-thread deadlock-free mutual exclusion scheme using mutexes like we can build with CAS can be implemented with just theta 1 space. And you can think of the proof as just some simple code that does it. So we can build a lock with compare and swap using just a pointer to an integer in memory. So our lock is just going to be a value stored in that integer. It's going to be a bool that's either true or false. True meaning the lock is currently held, false meaning it's currently free. And to perform a lock, this is basically a spin lock using compare and swap. We're going to say, come in, compare and swap the lock with the old value false and the new value true. So if the lock is currently false, this compare and swap will succeed. We'll atomically set the lock to true. So we'll lock it and we'll fall out of the loop. If the lock is currently held by somebody else, the value is going to be true. And so the compare and swap is going to fail. And we'll repeat around spinning in this loop until the lock is set by somebody else back to false and we can claim it. And because this compare and swap, the check of the value and updating it with the new value is atomic, we are guaranteed not to have race conditions in this check and update. And then we can unlock just by simply setting the value in the lock variable to false. Okay, so now let's look back at a simple problem that we saw last time. Excuse me. So last time, one of the pieces of code we looked at synchronizing wanted to just do some computation on each element in an array and then sum up all the results. So we have some array of size n. We want to do a parallel loop over all the elements, all the n elements in the array. where for each one, we're going to compute some function of that element and accumulate the result of that computation into a single scalar result. We saw last time that an obvious problem with this just by itself is that we have a race on result. And that's because plus equals on most real machines, including our x86 machines, can't be implemented atomically. Plus equals is actually 3 separate operations. We have to load the old value of result, add something to it, and then write it back to memory. And if you think of interleaving multiple people doing this in parallel, if they all load one stale old copy, all add to it, and then all write, the last write's going to win, and nobody else's updates will have been actually accumulated into it. They'll all just get dropped. So this is a problematic race. Last time we saw how we could use a lock or a mutex to synchronize. A point we made then, we were talking about contention, was that it would potentially throw away all our performance. Last time we put the lock around the whole body of the loop. So we put the lock around this entire statement. If you think about it a little bit, we can do a bit better than that if we assume that the compute function is where most of the cost is, and this plus equals is relatively cheap. We can put the lock just around the plus equals, so we don't lock the whole thing. So we can still usefully do the compute stages in parallel. We're still going to have some contention on doing the accumulation, but we improve performance a little bit. But there's some other problems with this too that may make us want to follow a different strategy. So in particular, if we think about what happens if the operating system swaps out a loop iteration just after it acquires the mutex. So we have a bunch of parallel iterations of this loop, and one of those, they're all doing compute and then trying to claim the lock and accumulate into the result. And one of them gets to here, claims the lock, maybe starts computing, starts updating the result, but doesn't release the lock. And then it yields its processor. There's a timer interrupt and the OS context switches to something else. That lock is going to be held and nobody's going to be able to make any forward progress until that thread gets woken back up and can exit the critical section. So the typical time for a context switch is on the order of like 10 milliseconds, which is orders of magnitude slower than many orders of magnitude slower than doing this simple read, modify, write of an integer. So we're potentially wasting a huge amount of performance with all of our other processors just sitting idle, waiting for a whole timer tick. But if we think about it, all we really wanted here, we're using a lock just to get the property that the load, addition, and store all are performed atomically. So we want the load followed by the store, not to have anybody else come in and store over the thing that we loaded before we've completed replacing it ourselves. So a lock is a straightforward way of getting that, but it turns out we can get the same property without using a lock at all. So let's see quickly what we can do with a CAS instead of a full mutex lock. So we can implement a concurrent version of this same thing using a compare and swap like this. So we have our parallel for loop. At the beginning, we're doing the computation and storing it in temp just like before. But then to update the result, instead of using a lock, we're going to use a compare and swap loop. So we have an old value and a new value. And as we go around the loop, we're going to say the old value is equal to the value of result. We're going to read from result and hold our own local copy of it. Then we're going to compute the updated value as the previous result plus our newly computed temp result. And then we're going to try to write our new result into the memory address for the shared result variable using a compare and swap. So if the result is still equal to the old value, we'll know that it's safe. No one else has come in and updated it while we were in this step. So our update is basically happening atomically. We know that nothing happened between when we read the initial result and when we're writing the new one. If somebody does sneak in while we're doing this and change the result, the compare and swap is going to fail, and we'll go back around the loop and keep trying again until we succeed. If we think about one of the bad conditions I just mentioned, Now, what happens if the operating system context switches us off while we're in the middle of one of these iterations? It doesn't matter. This one thread is not going to be doing useful work, but there's no way for anybody to be blocking anyone else from making progress. There's no single shared resource, critical resource that can be held. So the algorithm is in that sense non-blocking, which is a nice characteristic to have. All right, any questions on this? Compare and swap is a really, really useful instruction, which if you're ever implementing your own concurrent data structures or even efficient things like mutexes on different platforms, you will find yourself often using. And so being able to think in terms of how this primitive can let you build little atomic update operations is a really useful technique. And even things like GPUs, it turns out, have instructions like this that you can use when doing massively parallel programming over thousands of threads at once, trying to do fine-grained updates. Okay, so CAS is a cool primitive that we can use to implement non-blocking block-free algorithms. So now let's see how we can use it to build a simple concurrent data structure without using any locks. I just showed how you can use it to do atomic updates like atomic addition without using locks. And now we want to build a slightly more complicated data structure. So last time we talked about a hash table. This time, built using chaining and linked lists. This time I'm going to keep it a little bit simpler, and we'll just look at a simple stack implemented with a linked list. These ideas will generalize, but it's easier to start simple in this case. So for our stack, we've got a node data structure. The stack is just storing int values in each element, and then each one, it's a singly linked list, so each one has a pointer to the next node, and then at the head of the stack, we have a pointer to the first element. So this is basic kind of data structure you've probably used in an early algorithms or your early programming classes. So we push onto the stack by inserting a new item at the head. And pop by removing the item at the head and making its next pointer the new head. So really simple. Now, this week we're trying to do this kind of thing concurrently. So we can make this concurrent by having a lock or a mutex guarding all interactions to the list. But our whole goal today is not doing that. And instead, it turns out that we can safely implement push and pop concurrently using compare and swap. So using our CAS instruction. So first, we can implement a push function that looks like this. So push takes in a new node and wants to stick it onto the head. But we want it to be safe to execute many pushes and pops concurrently without them leaving the list in some inconsistent state. So an atomic push can be accomplished by saying, take the new node, set its next pointer to the current head. So we're trying to insert onto this end of the list. So we know that we're going to be prepending before this element. So our next pointer is going to be the current head element. And then we're going to use compare and swap to try to make our new node the new head, so long as somebody else hasn't come in and changed what was the head from what we thought. So looking at how that actually works out concretely, say we have a new node here with the value 81. We're first going to set its next pointer to the current head. And then we're going to use compare and swap to atomically replace the head pointer now with a pointer to the new node. So in the case of just inserting one thing, this does basically the same thing you'd expect. But now let's think a little bit about what happens if we have a potential race between two concurrent push operations. So let's say in this case, we get one push of this new node with the value 33. It's going to set its next pointer to the current head. And then another insert races in, another push races in with this node value 81. It also sets its next pointer to the current head. And then the second node succeeds in the CAS. It runs the CAS first, and it's able to make itself the new head. Okay, so the insert of the first, so now the state of the stack is this. We have these three elements on the stack. And the push of 33 was in the middle of executing in this state. And now it tries to do the compare and swap. But critically, the compare and swap depends on the comparison of its current node next pointer with the current head of the list. If nobody else had raced in, these would be equal and it would be safe to update the head with the new node. But because somebody had beaten us to it, this next pointer is now stale. And so the compare and swap is going to fail. And we'll have to go back around the loop and try again. So then the second time around, when we try again, we reset the node's next pointer to the current head, which is 81. And then the cast can succeed and we prepend this other element to the list. All right. So that's basic atomic push with compare and swap. And now let's look quickly at pop. So pop is going to be somewhat similar, using a compare and swap to safely update the head pointer. So we're gonna, when we come into pop, we're gonna grab a reference to the current head. We have to have some extra guard here. This while current is gonna terminate the process if the list is ever empty. If current is null, that's basically what that's checking. So we're making sure that we don't, read off the end of an empty list if the list is currently empty or somebody pops off it before we get through our own process, pops everything off it before we get through our own process. But then the core update is in here. So we're going to try to replace the head with the next pointer of the current head, so long as somebody else hasn't raced in and updated the head before us. If we're successful, we'll break and return the thing that we popped. Otherwise, we'll set the current pointer to the new head at this point and repeat the process until we succeed. So concretely, when we come in, we have a current pointer, we set it to the current head, and then we atomically compare and we use compare and swap to atomically replace the head with the next pointer, so long as no one else has come in the meanwhile. All right, so that's everything we need to implement a lock-free push and pop on a stack using compare and swap. So quick side note about performance implications. So compare and swap in general is going to require acquiring a cache line in exclusive mode. As you remember back to our cache coherence protocol discussions, it needs exclusive access to the whole cache line that it's trying to atomically update, which means that it's going to invalidate that cache line in all the other caches. And the result is going to be really high contention on that cache line if we have a bunch of processors trying to do compare and swap to the same value or the same cache line around the same time. So one quick optimization we can use, we can introduce, is to first do a regular read, just a simple load of the value at the memory location, and check if it's changed before we do the atomic compare and swap. And so we only do the compare and swap if the value hasn't changed up until that point. So we can put that optimization into our atomic push and pop code, and it just looks like this. So we just added these two extra logically redundant checks, but that are basically just here for performance. So this check is that the head, checking that the head hasn't been updated, or similarly here, are basically quick checks to say if this condition were true, we know we would go back around the loop. We know this condition would fail, or similarly here. But they're just using plain load instructions, which work even if that cache line is being shared by multiple cores. So we're not going to be we're going to skip and try again without claiming exclusive access and causing that cache line to ping pong around the system unnecessarily. So this can be a useful low-level optimization in these sorts of schemes. Okay, so that's a simple lock-free stack using compare and swap. The stack case is really simple, which is nice because it's it's easy enough to just read through and carefully think through what could possibly happen. But it turns out that this basic style of scheme actually generalizes quite a bit. So there's lots of efficient lock-free algorithms that people have developed for a whole variety of classical data structures. So this was a simple interface to a limited interface to a linked list that you could just treat as a stack. But there's more general linked lists, queues, skipped lists, hash tables, I think B trees and other things that people have built decent lock-free algorithms for too, using similar sorts of strategies. Doing this in general is useful. So, if you're implementing some core data structure for a database engine or a highly concurrent server or something, you might find yourself doing things like this. But it's really, really difficult. These things are very difficult to get right, very difficult to debug. Debugging tools can't really help you with them often. So very often it's most useful to know that these sorts of things exist and build on top of libraries that provide them for you rather than trying to jump into the deep end yourself with this kind of thing. But fortunately, in C and C++ and other languages, people have built a lot of these things already. And many real systems you use may implement some performance critical components using stuff like this. So there's some theoretical complications. So in theory, there are potential issues with starvation with the scheme that I presented. Basically because of contention, there's no guarantee that any one, like from the perspective of one push, it's possible that it'll spin forever and endlessly get preempted by other people racing in and beating it to the punch. But in practice, this kind of starvation rarely happens, and generally not for long. And then the last thing about these sorts of lock-free concurrent data structures is, I just wanted to say, is that the idea of transactional memory, which we touched on very briefly at the end last time, is a richer concept than just these simple atomic instructions like compare and swap, a big goal of which is to enable much more powerful versions of these kinds of lock-free schemes, by allowing you to execute kind of arbitrary whole blocks of code atomically. But there's practical issues with all of these. Like I said, transactional memory systems at the level of high-level languages do exist. They have somewhat high overhead. At the level of raw hardware, real general transactional memory mostly still doesn't exist in the world today. And it's unclear when or if we're actually going to get it. All right. So now I want to wrap up with one specific problem that this kind of scheme faces. And this is one of the reasons why, well, in isolated contexts like that stack that I showed, it seems kind of tractable to build a lock-free algorithm yourself. There's a bunch of additional details that you need to worry about doing this in a real language like C that make it often non-trivially harder than what I just showed. And in particular, I want to talk about one related to memory called the ABA problem. So the ABA problem was introduced by 4 Swedish authors in the late 1970s. Or maybe not. So the ABA problem, not the ABA problem, is this. So let's say we start with a stack in this state. So thread 1 is going to begin to pop. So this is back to the stack example, the atomic stack example that we've been working with. So thread 1 is going to begin to pop the node here, the head currently containing 15. But let's say that it stalls after its first step, where it's read the current next pointer. So then imagine thread 2 comes in, interacting with the same stack, and it pops off this node containing 15. So it's going to cause this update. The head is now pointing to the next node, 94, and 15 is going to be freed, say. Thread 2 then pops off the node containing 94. So it does another pop, frees this memory. And then let's say thread 2 comes in yet again. It does a third update before thread 1 gets to complete its first attempt at popping. it allocates and pushes a new node, now containing the value 7, but when it called malloc to get that node, it got back the same piece of memory that had been freed a second ago containing the value that had the node 15. So now the state of the list is this. So thread 2 has pushed node 7, but is reusing the same memory for that node that was previously used for the head of the list, the head entry that had 15, when thread 1 had started its process of trying to pop. So now if thread 1 resumes, we're going to run into a problem. And that's because the atomic check that thread 1's going to do is saying, is my current pointer the current list's head pointer? Conceptually, that was meant to say, is my current pointer up to date? Has no one else come in and updated the list out from under me? But if we're just doing that check at the level of pointer value equality, and we somebody else like thread 2 here had reallocated something back to that same address and inserted it back onto the head, then thread 1's check for pointer equality is going to come back true, and its compare and swap is going to succeed. So thread 1 had previously gotten this pointer to the node 94 as the next pointer, and it's only, its compare and swap is going to be saying, if this is still a pointer to the same place in memory that I saw when I started at this first step 1, then we should atomically change the head to point to what was the next pointer when I saw it. But in this case, hopefully it's obvious that that's a problem. So thread 1 resumed, thought that no one had stepped in, and as a result, its cast succeeds, and it's inserting garbage into the list. So this is a deallocated entry that's no longer supposed to be there. So the key thing here is that the compare and swap can't distinguish between the actual old value and the replaced value, because it's just doing its comparison on the basis of pointers, and it's perfectly possible for those pointers to get recycled by our memory allocator, for example. So there's a few ways we can deal with this. So some architectures provide an even richer instruction than compare and swap, something called load linked store conditional. So load linked keeps track of the location. And then if anything, so it's basically a pair of instructions. Load linked keeps track of the memory location. And then if anything happens to that location, the store conditional will fail. So it's a slightly stronger guard rather than just checking atomically for pointer equality. So if any updates to the load linked address have occurred, then the store conditional is guaranteed to fail, even if the value read by that load link has since been restored. So load linked store conditional is stronger than a read followed by a compare and swap. Even just using compare and swap, there's a bunch of schemes we can employ. So we can, instead of atomically checking just tracking just pointer values, we can track a tuple as long as it's small enough that it can fit in a word that our hardware is able to atomically compare and swap on. So we can keep like a version number along with each pointer that we update. So we increment the version number every time the pointer is changed, and then our compare and swap has to operate on a contiguous set of memory that's both the pointer and the version number as a single atomic unit. There's a bunch of issues with this. One, tracking these version numbers is kind of a pain. The version numbers might need to get arbitrarily large, and if our pointers are already 64 bits, like maybe we don't. We can get clever and know that only 48 or 52 bits or something of that are actually available as usable virtual addresses on our machine. But that still doesn't leave that many bits to track versions. So these may not fit into a word, fit together into a word that we can deal with atomically. And then there's other schemes we can use on kind of the memory management side to try to prevent this type of node reuse, so long as any outstanding interactions exist. So we could prevent the memory of node 15 from being used as node 7 while thread 1 was still executing. But as you can imagine, this winds up requiring complicated synchronization with our memory allocation scheme and other stuff like that. So it all gets pretty complicated pretty fast. So that's it for today. And that's our tour through non-deterministic parallel programming and a little taste of lots of the fun things you can do. And with that, thanks. We'll hang around for questions.